Problem number 3 is asking you a few different things in this case. So we'll start with part A, we'll work our way through part B and part C. So it gives you two curves, R1 equals 2 plus 2 cosine theta, and R2 equals 3. The first question says that it wants you to graph the pair of polar curves on the same coordinate plane and identify the curves as R1 and R2. So let's go ahead and let's graph them. So first off, what I'm going to do is I'm going to find values that I can plug into a graph. So I'm going to make a theta, I'm going to make an R chart. And now what I'm going to do is first off, I'll look at R1. So I'll actually call this chart R1, theta and R1. So R1 is equal to 2 plus 2 cosine theta. So if I set R1 equal to 0, I can figure out where its zeros are. So if I set this equal to 0, I end up getting cosine of theta equals -1. So cosine of theta is equal to -1 at pi. So I'm just going to go ahead and denote that pi is one of my zeros in this case for here. Now I'm just going to plug in some points around it. Pi over 2, 0, 3 pi over 2, and 2 pi. And I can get values for that by just plugging into the equation. So if I plug in 0, I end up with a radius of 4. If I plug in pi over 2, I get 2. 3 pi over 2, I get 2. 2 pi, I get right back at 4. Now I'm going to make another column here. I'm going to call this R2. So I'm just going to use the same values for R2, and the reason is because this actually isn't that hard of a shape to graph. R2 equals 3 is just a circle with a radius of 3. But I'll go ahead and make some points just to be sure. So if I plug in R2 equals 3, I get 3, 3, 3, 3, 3. So we're sure now. Cool. So let's go ahead, let's make our graph. Now, R in theta, so I'll graph R1 first, and then we'll figure out where R equals 3 is on this plot. So at R1 equals 4, I have theta equals 0. So I'm going to call that point out there. It's going to be my R1 equals 4. This is going to be a radius of 4. Comes back into a radius of 2, so I'm going to call that somewhere in here. We are going in this direction because we always move counterclockwise like the unit circle. At pi, I come back to the origin. Cool. 3 pi over 2, I go back to a radius of 2, so again, that's about right here. I'm going to try to make this as symmetrical as possible because they are polar graphs. And 2 pi, I go right back out to here. Great. And we're moving in that direction, even though I graphed it from the other way. So that's R1. Now we need to find R2. So I'm going to denote R2. I'm going to call these points here. This is going to be my radius of 3. Now this is probably going to be a little bit axisymmetric, but again, I'm only looking for close enough in this case. And again, sometimes it's hard to draw circles, and I am no artist. But I will try my best. Yep, that was pretty terrible, but at least we have a general sense of what the shape is going to look like. So this is going to be our R1, R1, this is going to be R2. Great. So that answers question A. Question A just wanted you to graph them. Good. Now we did that. Now, the next question says, label the rays theta of intersection of the two curves. So let's start there. Let's find the intersection points of these two curves and let's label them. So to find the intersection points, all we do is we set them equal to each other. So when I set this equal to this, I end up with 3 equals 2 plus 2 cosine of theta. Cosine of theta is equal to 1/2. So I need to find where cosine theta is going to be positive 1/2, and that will be my theta values for my intersection. So I already know that it will be positive in the first and fourth quadrant. So theta is equal to, this should be pi over 3, because again it would be where it's closer to the top part, and it should also be 5 pi over 3. which would be in the fourth quadrant. Good. So, now that we know those values, I'm going to draw my little rays. So there's our first intersection point. This is theta equals pi over 3. I'm going to draw my other one here, and again, not a very good artist. Yep, I missed it completely. I'm going to call that the intersection even though it's right about there. And this will be theta equals 5 pi over 3. So these are our intersection points. And we had to label them on the graph. So now our graph has these two intersection points. And the points r theta, where r1 intersects the origin, the x-axis and the y-axis. So now what we need to do is we need to look at just r1 and figure out where the points are where it intersects either the x-axis, the y-axis, or the origin. And based on our graph, we have 4 points where it does that. But luckily enough for us, we know those 4 points because we already made our chart, we already wrote them out. So let's go ahead and figure out where those points are. So I'm going to label this point A, I'm going to label this point B, I'm going to label this point C, I'm going to label this point D. Sorry, that is a D. It's in dog. So A, well, that's all the way out here. I know that that is 4, 0, because remember we're writing as r theta. B is going to be equal to pi over 2 and 2, so 2 pi over 2. C is going to be equal to 0 and pi, so this is where it intersects the origin, so 0, pi. And D is equal to 2, 3 pi over 2. So there we go, we have our points. And those should be all the points we need. So that question wanted us to just label those on the graph, so I denoted them as A, B, C, D, and I have the corresponding values right here. I also have the rays of intersection at pi over 3 and 5 pi over 3. So that's good. That's all we needed in that case. Now, part C wants us to set up the integral used to find the area inside both curves of R1 and R2, but do not evaluate it. Okay, cool, so let's go ahead and do that. So first off, we need to figure out where the area is that lies inside of both curves. Well, okay, so it looks like in this case we might have to split this up a little bit. So we do have an axis of symmetry along the x-axis, so that's good. So if there's an area over here that overlaps, it should overlap here as well. Okay, so right off the bat, I notice that area that's inside both curves is inside of this block right here. So this is inside of the circle, and it's also inside of this curve. Okay, so that's going to be my first stop in this case. So what I'm going to do is I'm going to say that the area, which is 1/2 r integral of r squared d theta, okay, so this is the formula that we're going to try to plug into to try to solve this. So I'm just going to erase our little chart over here so we can get a little more room. So when I plug into here, I know that if I want to get this area right here, my radius would be tracing along the curve for my circle. So I'm going to denote that as r2 squared d theta, which it says in this case we can leave it in terms of r2 and r1, so we don't actually need to plug anything in. But if you did, you probably wouldn't get points taken off. So r2 squared d theta. Now I do need to figure out the bounds, and also I do need to write a 1/2 here. So my boundaries in this case, well, again, I know there's an axis of symmetry this way, so from here to pi over 3 will encompass that area along this curve. So if I integrate r2 from 0 to pi over 3, that gets me the part of the area I need. And if I want to account for this extra piece down here, that also should be the same because, again, it is inside of both curves, just reflected across the axis. All I need to do, I just need to multiply this by 2. So I'm going to multiply by a 2 out here. But we're not done. So this area was inside, but this area over here is also inside. So why didn't I account for that when I integrated from 0 to pi over 3? Well, if you measure from the origin outward to see where your radius is hitting, it's no longer hitting the circle, it's actually hitting the cardioid. So therefore, R2 is no longer my radius function. My radius function is now going to be R1. And to figure out where that's from, let's go ahead and write 1/2 integral R1 squared d theta. So again, I'm saying that from here to here, I'm tracing around R1. I know that that starting point right there is pi over 3, and if I move all the way back, I move back to pi. Because I know that this was pi over 3, that was the intersection point. This is pi over 2, and back to the origin, if I still had my chart up here, would give me 0. So I'm going to trace from pi over 3 to pi in this case. And again, this area down here is also reflected. So therefore, if I include this in the multiplication of the 2, I can get this area and this area from this equation multiplied by 2, and then I can get this area and this area from my first equation multiplied by 2. So therefore, when I look at my final answer, I see that it should match exactly. Good. Now there probably is a couple different ways you could write this, but in this case, this would be sufficient. Remember, you don't need to simplify anything in this case, nor do you need to plug in and solve it. All it's asking for is it's just asking for the representation.
The Teaching Center, UF's Learning Resource Center.